All right, Maxim, ready?
Yes, yes.
So to invite second speaker of today, Professor Maxim Grigoriev from Lebedev, and he'll tell us about interacting gauge fields from quantized spinning particles. Welcome.
Okay, it's a pleasure and honor to have a possibility to give a talk at this conference, and thanks to organizers for inviting. I'll talk about approaches to derive interacting gauge theories from quantized spinning particles, which are somehow, these approaches are inspired by string field theory. This work is based on something which should appear hopefully soon with Adiel Meyer and Eva Sachs, but also it will be a bit of an overview of such methods, and it will also cover some earlier works more in the context of high-spin gauge theories, which were performed in particular in collaboration with Xavier Bicard and Zhenya Skvortsov. Okay, so what are motivations? So what we know from string theory, this is some sort of standard paradigm there, is that fields of string field theory, strictly speaking, are background fields on which string can consistently propagate, and this consistency gives us the gauge transformation for these background fields, and this consistency also gives us the on-shell conditions, the equations of motion. It is a famous story how Einstein equations for the background metric appear from quantum consistency of the string. However, although the string is defined on this background, and all these fields are background fields, we should expect naively background independence of the theory. But in fact, it's very difficult to achieve it in this way, if possible, because even to define quantization of a volt sheet, one needs to actually specify background geometry, because we don't know how quantum strings behave on generic backgrounds. And I'm not going to talk about string theory. This was rather an inspiration. So what I'm going to do is to consider simpler models, namely particles and quantum particles, or more specifically spinning particles in general, and see if this ideology, to which extent this ideology may help us to construct sensible models. And the familiar example, which was already discussed on this conference, is, for instance, the conformal higher spin field theories, and the conformal higher spins can be seen as background fields for quantum scalar particle in the minimal version, and this and then the on-shell conditions arise from the induced, so-called induced action, or log divergent terms, what one can see in different ways. In fact, starting from the same particles, particle model, what one can do is to put these background fields on shell by using holography, by somehow moving the theory from the boundary to the bulk, because off-shell fields on the boundary are somehow one-to-one to on-shell fields in the bulk, and this is quite a fruitful approach to construct high spin theories in ADS. Unfortunately, in ADS, we know that these theories are not quite well defined because of locality issues. So it's again very difficult to make a precise statements and compare this, for instance, with Vasiliev theory, etc. But there is a totally different approach initiated by Ziegel and co-authors, who succeeded to show that, for instance, if we consider superparticles and do something and relax a little bit in a certain sense the conditions, we can extract Young-Mills, well, naively Maxwell, but then tensoring with matrices with gauge algebra. One can extract Young-Mills equation from the quantum consistency of this n equal to superparticle, and this idea was recently generalized to the case of gravity, and by Roberto Bonezzi and co-authors of this work I'm talking about, to show that n equal 4 superparticle with proper reductions, restrictions, etc. gives Einstein equations and possible generalizations. So the aim of my talk is to describe this framework, briefly explain how this works for these higher spin models very briefly, and then concentrate on identifying this string field theory-like framework for n equal to superparticle, and build this and show how this algebra how this can be made precise, and what are background independent algebraic structures which lead to background independent formulation. So it's at the end of the day, I believe what we can arrive at is sort of toy model for string field theory, which is in a proper sense of the word is background independent. Okay. So let me begin with recalling what is the first quantized BST approach, because it is very instrumental in this business. So we start with the quantum constraint system, quantized in BST approach. So the representation space is wave functions on our space-time with values in a certain graded space. The degree is Gauss number, and different elements corresponds to elements of different degree corresponds to physical fields, antifields, ghosts, and all this BST machinery. BST operator is a differential operator, matrix valued, which act as a differential operator on X and as a matrix as a linear operator on this internal space. It squares to 0 and is of degree 1. Physical fields are found in degree 1 in representation space. This is, of course, a convention. Often people take it 0 or something else, but for me, it will be convenient. You can always shift. For me, it is convenient to have them in degree, to use convention where physical fields are in degree 1, gauge parameters in degree 0, and other guys, for instance, gauge parameters sit in degree -2, etc. And then what we can do, we can give a field theoretical interpretation to this quantum mechanics. This is relativistic quantum mechanics. I didn't even introduce Hamiltonian. So from first quantized point of view, it's reparameterization invariance. So Hamiltonian vanishes. We have only constraints, means BST operator. And equations of motion are simply physical conditions for the fields, and these equations are invariant under this gauge symmetry, so phi -1 are indeed a gauge parameter. If there is an invariant inner product on our representation space, then all this follow from the action, which is gauge invariant, and have the familiar phi omega phi structure, and this is actively used in constructing at free level both string field theory models and higher spin models. And the physical meaning, of course, is that if we start with such a quantized particle string, then such an action is going to describe classical theory whose excitations upon quantization are going to describe these particles we started with, roughly speaking. Okay. So the standard example, which all of us know, I am sure, is a just relativistic particle. The phase space is just like that. For some reasons, it doesn't want to. Well, anyway, it's. Sorry, just one moment. There is something wrong with my stylus. No, it's. Well, okay. Do you hear me? Is everything fine? Hello.
Below. Okay, now it's all back.
Yeah, it was, I don't know, there is a problem with my stylus, so maybe I should. Set. Sorry, there is a technical issue which I don't quite understand what's going on. Let me try to use the different application which I'm more sure about. Do you see my screen?
Yes.
Okay, I'll use different application because it was something wrong. It's not so nice, but okay, so we are at discussing relativistic particle. Okay, so this is an operator algebra. So we have space-time coordinates and momenta. Only mass shell constraint means one pair of ghosts. Generic state has the following structure, and the terms proportional to ghost is interpreted as Bartelme-Vilkovisky antifield, and phi is a physical field. BRST operator just imposes the mass shell constraint, and we get Klein-Gordon equation as a condition, as a BRST invariance condition for the state, as it should be. The next thing is, how do we describe interactions in these terms? Interactions are described, of course, they correspond to some nonlinear terms. And algebraically, this means that we introduce maps mu2, mu3, etc., each of them having such a ghost number, and the consistency of all these, of all omega together with these maps, all these maps are defined on the representation space boldface H, is that all these guys equip H with the structure of L-infinity algebra. And in a particular case where only mu2 is non-vanishing, this is just a differential graded algebra. And the L-infinity conditions tell us that omega is nilpotent, and omega differentiates the mu2. Note that mu2 is a sort of algebraic structure on the representation space. It like defines multiplication of states. Yeah, and I forgot to put here in this case, it should be Jacobi. I forgot it. It should be here for this this algebraic structure. Okay. General case where all mu's are non-vanishing, or more than two, is better handled in the language of BV, which from this perturbative point of view can be thought of as a generating procedure for this first quantized description, and it is obtained by replacing fields with components of our wave functions with graded fields, which are now not necessarily real valued, but they are coordinates on a graded manifold, and packing them into an object called string field, which is very convenient. And in terms of this string field, the BRST differential, which is a differential, first order differential operator on the space of fields, is defined as follows. And its nilpotency precisely encodes the L-infinity relations for the underlying maps. In fact, these maps, omega, mu2, mu3, etc., are just Taylor components of this differential. Of course, the BV approach is more general than L-infinity, but in particular case of perturbative theory, they are one-to-one. But nevertheless, if we are interested in perturbative construction of theories, then this L-infinity description is quite instructive. And in fact, it was developed precisely in the context mostly by Zwiebach, if I understand correctly, and also some mass people, by precisely with the aim of constructing interacting string field theory. Okay. And another important issue here is the background independence. Of course, because we talk now about a perturbative construction of interacting gauge theory, we could only we don't have background independence, because our omega determining the quadratic piece in our action in fact is a background, if you want, because it contains information about background metric, etc. So at least in a manifest way, we can't realize the background independence. And background independence means that all fields of our theory are dynamical and governed by the equations of motion and gauge transformation or action. However, in this setting, if we can succeed to find such a specific vacuum, non-trivial, such that it acts, its action with respect to this algebra structure mu2 reproduces the action of BRST operator, we can subtract, we can change the vacuum, we can change the, we can redefine fields by this non-trivial vacuum in such a way that the action takes purely cubic form, and it depends only on mu2. You see, omega is gone from the action. Omega is only a particular solution for this action. And this is the famous purely cubic action of string field theory, for which equations of motion is simply the nilpotency condition. And of course, the main message is that master equations, the nilpotency condition is to be understood as equation of motion. If you want something background independent, that's what we really want, in fact. Unfortunately, on these works in string field theory, only at a very formal level, nothing is defined. And the main problem is that mu2, in order to define mu2, you already need to specify background, precisely because you can't quantize string on the generic geometry. Okay, so this tells us that we should probably take another route and try to start with something whose equations of motion are immediately nilpotency condition. And it's, of course, the same story. We start with constraint system, but interpreted differently. If we have a quantum constraint system, the idea is that implicitly what happens is that constraints are imposed on physical states. And we have a consistency conditions that constraints form an algebra. And we also have an equivalence relation for constraints, because we know that we could redefine constraints. They still describe the same constraint surface, and we can also do canonical transformation of constraints in infinitesimal canonical transformation of constraints in the Hamiltonian setting. So the idea is to treat constraints as generating functions for fields. For instance, if we quantize everything in coordinate representation, we expand f in powers of momenta, and we can interpret the coefficients as space-time fields. But then this becomes equations of motion, and this becomes gauge symmetries. Gauge symmetries. Of course, if we reformulate it in BRST language, these conditions become and build a BRST operator out of constraints f. We arrive at a master equation as an equation of motion, and natural gauge symmetry of master equation as a gauge symmetry. But now psi is a parameter. But now omega is a generating function for background fields, which is compatible with the previous discussion. But don't be confused, it's a different omega, strictly speaking. If there is an invariant inner product, it should have Gauss degree -3 in my conventions, and we can in principle build the action from which this equation follow. And in contrast to string theory, this procedure is well defined for quantized superparticles, unfortunately without additional steps. It only gives off-shell fields. So you get equations which are equivalent to constraints, but what is not trivial, you get a nonlinear gauge symmetry. So nevertheless, you get in some sense, you get a nonlinear theory, And this nonlinearity is mostly thanks to this nonlinear gauge transformation law, which is linear in fields and linear in parameters. But it means it is nonlinear because linearized gauge transformation does not depend on fields. Okay, and still the same example, scalar where phase space is xp. This is a generic constraint f. It expands in terms of totally symmetric tensors, which starts with scalar, spin 1, spin 2, and higher spins. And gauge transformation gives us there are actually two gauge parameters. One, these are generalized diffeomorphisms. These are generalized Weyl transformations. And in fact, what we are dealing with is a nonlinear completion of gauge transformations of Raskin-Zeitlin fields. This was observed in this high spin context by Segal. And this is precisely the starting point of his construction for the theory. Before saying a few words about this theory, let me say that there is a nice degree, natural degree on this operator algebra, which allows to extract low spin sector. If we decompose degree, if we introduce degree like this, then degree, the subspace of elements of degree less than 1, which I call filtration 1, because there is an associated filtration on the algebra, is a Lie subalgebra. So there is a consistent theory associated to it, and this is precisely the theory of low spin fields, which is gravity plus spin 1 plus spin 0. And indeed, the standard vacuum, this guy, is just which corresponds to just p squared constraint, it precisely has degree 1. Okay, in these terms, one can construct the Segal-Zeitlin theory of higher spins. What is remarkable that this is sort of inspired by the Sakharov construction of induced gravity, where gravity arises as an effective theory when we integrate over the matter field. So we treat this wave function phi as a matter field. We construct effective action. In general, it is divergent, and the log divergent term is gauge invariant and gives the action of this conformal higher spin theory. But in fact, there is an alternative approach to build on-shell fields out of these off-shell guys, and this has to do with the holography, because one can think of these conformal off-shell fields without doing effective action as boundary values of on-shell fields in the bulk. We know they are one-to-one with properly defined boundary conditions, and there is another fact from the theory of local gauge systems that in fact the theory is determined by the knowledge of on-shell gauge transformations. But we do have nonlinear on-shell gauge transformation, which we can somehow map from the bulk, from the boundary to the bulk, in order to arrive at on-shell theory in the bulk. And this is sort of explanation of what Vasiliev high spin theory is. Again, you can't really make it fully explicit and well defined, because once you go with these tools to the bulk, you immediately meet some sort of non-localities, and different formulations are not so easy to relate. But in principle, you indeed could extract needle structures, and in the same way to construct new type of higher spin theories. Okay, so much for off-shell and higher spin fields. So let's go to a different story where we don't have higher spins, where we don't use holography or induced actions. And as was shown by these gentlemen, it is still possible to extract on-shell fields from quantized particles, but what you have to do, first of all, you need supersymmetry. You need a supersymmetric particles. And second, you need to, in a certain consistent way, relax a master equation. So what is this relaxing? In fact, it is very well known. It can be interpreted as a well-known procedure known as a constraint reduction or quantum Hamiltonian reduction of operator algebras. And the idea is very simple. If we have an associative algebra and its module, of course, we have in mind graded algebra of quantum operators and the representation space. And suppose that for some reasons we are interested only in the subspace H naught. think of it as a physical subspace singled out by constraints. Then what we can do, we can consider a subalgebra of elements which preserve the subspace. And then it contains an ideal of those operators which act trivially on the subspace. So finally, what you can do, you can take a quotient. And this is, of course, quantum constraint reduction. And this is precisely how algebras of symmetries or quantum observables arise in practice. And in particular, the familiar high-spin algebras are precisely of this form. And as I mentioned, the next ingredient is supersymmetry. So the simplest example, non-trivial in this sense, you can still consider n equal 1, but this leads still to off-shell fields and this type B high-spin theory. But the first non-trivial example in this context is n equal to supersymmetric particle. So in addition to space-time and moment, to introduce fermionic thetas and constraints with bosonic ghosts, and mass shell constraint is unchanged, just like in n equals 0 case. You pick a representation space where the initial baristi operator is describing the vacuum, act like this. But in fact, we can describe in this sense, in this setting, generic geometry. Do you see now?
Yes.
And where it was it here or?
No, go back. It was here. It was here. I can next slide, I guess. Yeah. Next slide.
Okay. Yeah.
So let me tell you that actually this formula in blue, you started to draw your circle in red, and you didn't finish to draw it.
I see. Okay. Sorry. Okay. But then things are not so bad. If I may have 3-4 minutes, I can finish. Is it possible?
You have 3 minutes.
Okay. Very good. So, okay. So we have this n equal 2 particles, and we have a spin one subspace, which we can use to describe the reduced algebra, and then we build the gauge theory associated to it with equations of motion is nilpotency by imposing again the degree the filtration 1 component is a Lie subalgebra and gives a consistent theory of low spin fields. And in fact, going through components, one can find that in the sector of filtration 1 corresponds to gravity background, which is non-dynamical. In this setting, we get Maxwell-Dilaton system where dilaton is off-shell. There is a non-abelian generalization which is easily obtained by tensor with a universal enveloping algebra, which surprisingly have exactly the same type of filtration. So there is a total filtration which allows again to build a Lie algebra of filtration 1 elements, which already with some extra restriction produce Young-Mills equations. And you can also analyze the sector of filtration 1, which contains gravity, off-shell gravity, and generic metric can be incorporated, but it is not dynamical. For n equal 2, there are no equations on the gravitational background, but still the system is background independent. Okay, this step I probably miss because it's just about quadratic Lagrangians, which can be built also, but in general, the problem of constructing full nonlinear Lagrangian, this formalism is open. It's not quite clear how to do it. And in this way, I arrived to my conclusions. So using this approach of graded algebras, quantum observables, etc., this is a fruitful in string theory, high spin theory, and the usual low spin models. So we succeeded to construct a background independent toy model of string field theory with finite amount of fields. Of course, it's some sort of refinement of the Ziegel model, but still it contains some new background independent algebraic structures, which actually ensures the background independence, including the operator algebra, this constraint reduction, and the filtration. They are all background independent. To define them, we don't need to pick a particular metric or other background fields. And what are open problems? Open problems are to give an exhaustive description of spectrum. To tell the truth, it's not fully done in all filtrations. We only fully considered the filtration 0. And one can also try to go to n=4 to include dynamical gravity in the spirit of the work of Banetzi, Meyer, and Sachs. And another interesting story is to maybe merge this with higher spin story, because there are no the higher n. These algebras associated to higher n particles are known also in higher spin theory, and in particular to n=2, if it is conformal, one can associate type C higher spin theory. Okay, so thank you very much, and I'm terribly sorry apologize for this technical issue.
Thank you very much, Maxim.
Somehow. Okay, thank you very much. I'm done.
Yeah, thank you, Maxim. We have time for one short question, please. I mean, if there are long questions, we postpone.
There are no other questions. So let me ask if there is some time. So just about the conclusions and open problems. So can you please comment on that, whether your one of your models that you have considered are on shell, I mean, on the field equations, or it's just off shell story? That's first half of the question. And second, about can you go to conclusions, please? You have this filtration somewhere. So does this filtration correspond to different field equations? Algebraic filtration, does it correspond to different types of theories with different field equations? Like
okay,
box squared and so on and so forth.
Okay, so first part. So this model is, let's say, both off-shell and on-shell. So in the minimal version, for instance, gravity and dilaton are off-shell, so generic, no differential constraint of them, while spin 1 is on-shell, Maxwell or Young-Mills. So in this sense, it is on-shell model.
You mean the same model or different models?
There is of course, there are versions of the construction.
No, I'm asking, is this within the same model that you have spin 1 on shell and spin 2 off shell, or these are different models?
It is the same model, but of course it's a matter of choice. If you want to separate background, you can say, okay, my degree 1 part is not dynamical, I fix it once and for all, then it is just a Maxwell-Dilaton system or Young-Mills. So it is perfectly on-shell. But if you want background independence, you need to allow all fields at the equal footing. And then you see that some of your fields are off-shell, some of your fields are on-shell. That's what happens.
That's frankly,
stop discussion at this point. We have to move on. So let's.
I agree, Sergey. Yeah, this is too much for a short question, right?
So let's postpone further question to discussion session. And thank you very much, Maxim, again.
Thank you, and again, sorry for
All right.
this
That's fine.
problem.